Good morning. If you can hear me, welcome. I know there's a lot of people joining in. I will give it about another minute to make sure we get everybody who is coming to the webinar into the webinar. And so we will start up in about 1 minute.
Okay, I'm going to check the power here. No, we're not going to. Hold on. Just hold on a sec. That's better. Okay. Share screen. There we go.
Okay.
All set.
Hello, everyone. All right. Bob, can you hear me okay? Everybody
Yes,
ready?
I can hear you.
All right. Perfect. Hi, my name is Bill Griffin, Professional Development Manager at Informs, and welcome to our first webinar in our sponsored webinar series. Today's webinar is entitled Adding Optimization to Your Applications, AMPL's model-based approach to fast development and reliable deployment, led by Bob Forer of AMPL. Bob is co-founder and president of AMPL Optimization and Professor Emeritus of Industrial Engineering and Management Science at Northwest University. Bob will present, and we will reserve the last 15 minutes of today's session for Q&A. Feel free to submit questions via the Q&A function in Zoom, and we'll ask them at the end of the presentation. Without further ado, now I'll turn it over to Bob. Bob, take it away.
Okay, good morning. Morning. So here's my status here. So I was at Northwestern University for over 30 years, and about 2012, I turned my attention to AMPL optimization full time. As you can see from the title, I'm talking about optimization, and I'm going to start by saying some things about what I mean by optimization and where that fits, and then I will introduce the model-based approach and have some comments about fast development and reliable deployment. And then the last part, I will show a variety of case studies to illustrate what can be done with this approach. So if you type optimization into Google, what it shows you is mathematical optimization, actually a Wikipedia article on that. And if you look at the article, it has a rather long description. In fact, it says that if you type optimization into Wikipedia, it redirects you to this page. And if we enlarge this description here, we see that it has various definitions of optimization. This one here that I've underlined is more mathematical, maximizing or minimizing real functions, input values, etc. But it also has other definitions, selections of best element from available alternatives, or finding, quote, best available, unquote, values of some objective function given a defined domain. And so you see there's a mix of more mathematical and more practical approaches. So let me say what I mean by a practical optimization. Okay. I feel that it comes up when you have a recurring need to make a large number of interrelated decisions, whether they're purchases or production amounts, assignments, anything that too many decisions to just make them by hand. And you want to consistently make highly desirable choices. Given this recurring need, each time you want to make highly desirable choices among these decisions. And to do this, you want to apply ideas from mathematical optimization. And these will be ways of describing problems or formulations, and ways of solving problems or algorithms. So there's mathematical optimization in what I call optimization, but there's also a fair amount of practical problem solving. Now, this describes sort of a practitioner's approach to optimization, but what's it mean from the sort of product, from the project management viewpoint? Well, here's sort of the steps of an optimization modeling project. Okay? You start off communicating with the client, you build some model or method to do the optimization, you prepare various data scenarios, you solve various cases, and you analyze the solutions you've gotten, and you report various results. And those are the sort of the steps, but this leaves something important, really important out. That optimization modeling is not just a one-off thing where you just do all these steps and you're done. It's a cycle. And when you get to the end and report your results, you invariably find that things are not the way they're supposed to be. There are complications. And so you go back and you communicate again and you discuss it and you add things and you modify things. And basically, developing an optimization model involves going around this cycle quite a few times before you get something. And so that's where, in my title, the fast deployment, development and reliable deployment come in. That's what you want in order to carry out this optimization modeling cycle successfully. From the practitioner's point of view, you want to be able to do this cycle quickly and get some results that the client will actually accept before they lose interest in the problem. And then you want to be able to take the model that's now working pretty well and deploy it in some way so that it can actually be used by people who are not experts in optimization. And then, well, things still are going to change. So you want to be able to make updates as needed. And so practitioners have these needs, and corresponding to each of these needs is a need for the software. So to repeat the cycle quickly, the software must promote fast prototyping. To deploy reliably, the software must facilitate integration with application systems. And to give you these updates, it has to be designed so that it encourages long-term maintenance. Okay? People can come back to it and modify it. So then, here now, that's sort of my introduction to optimization very quickly in 5 minutes. And now I'll give you an overview of the rest of the webinar. And the theme of this webinar could be said as consider modeling, not programming. Or modeling as an alternative to programming. I am, after all, talking about model-based optimization. And in order to put this forward, I'm going to do it in 3 parts. Each one of them is going to be a comparison of 2 approaches. One approach more model-like and one approach more programming-like. So I'll first talk about 2 approaches to optimization itself, and then 2 approaches to model-based optimization, and then finally 2 approaches to the modeling languages that are used in model-based optimization. And when I'm through all of that, you'll have, I hope, a pretty good idea of the value of model-based optimization and how it's used. And then I'll conclude with 4 case studies to show what happens when people actually put this into practice. So then let's start with approaches to optimization. I said there'd be 2 approaches. And one is a method-based approach, and that's essentially that you program a method or an algorithm for computing solutions to your optimization problem. And I'm contrasting this to a model-based approach where you formulate a description or a model of the desired solutions. Okay? Now, how am I going to decide which of these you should prefer? Well, for simple problems, actually, I could argue that any approach is easy and doesn't matter that much. Okay? But the truth is that in real optimization problems, there are complications. And that goes back to this optimization modeling life cycle, that you have to keep going back and changing things till you get it right. And every time you change it, you add more complications that your client needs. Okay? You change things, you add things. And so in real optimization problems, they're just not so simple. And so since they're not so simple, actually the approaches make a difference. So let's start with a simple example that I'll use to contrast them. And this is just an example where I want to ship products efficiently. And the context is I have a transportation network. Maybe it looks like that. And I have some various locations represented by circles and links, which are shipment links. And supplies come in at some places, demands at other places. And I have various capacities and costs. So there's a simple but not entirely trivial model. In the case where I want to do some optimization. And the key is I want to decide how much of each product to ship on each link so that the shipping costs are kept low, but I meet all the requirements, okay? I respect the capacities and I respect the supplies, I meet the demands, I balance shipments at every node, okay? And now I can describe the two approaches in terms of how they would approach this problem. So a method-based approach would program a method to build a shipping plan. And a method is sort of says, how do you compute a solution? So you actually write a program to compute a solution that determines how to do it. And there are various approaches. You could think of orders. You could come up with rules for meeting each order and then fill orders one by one according to the rules. You could imagine routes. You could pick a good route from a supply to a demand and then try to fill it as much as possible to meet a lot of orders. And then once you do all this, you can refine this in all sorts of ways. You can enhance the methods to be more clever about them. You can take the first solution you get and improve it by looking for various local improvements. And then you can apply all sorts of concepts that are what are called meta-heuristics, so they're actually broader ideas for improving solutions and moving from solutions to better solutions. And I've gone through this very fast. There's actually been lots of thought about how you might program methods for optimization problems. And I could easily spend a number of slides going through the various approaches. But what I want to do is contrast this sort of thing with a model-based approach. And in a model-based approach, you don't think of how to solve the problem, you think of how to describe the problem. You want to formulate a minimum cost shipping model that says what a solution should satisfy. So you identify the decisions, the amount shipped, which are called your variables. You specify what shipment amounts are going to be allowed by writing various equations and inequalities, which are called constraints. And then you write out a total shipping cost as a sum of all the costs. So you describe what your answer ought to satisfy without saying how. And then you collect all the costs and capacities and supplies and demands in your data. And given this description and one scenario of data, you have an optimization problem. Then what then do you do with it? And what you do with it is you send it to an off-the-shelf solver, which computes solutions. So you don't worry about how to solve the problem. You use a powerful tool that somebody else has developed that's available, ready to run, and will take the problems. And the great thing about solvers is that they handle broad problem classes. So all sorts of problems that you might formulate will be handled by one of just a few classes of solvers and in an efficient way. And they become much more efficient over the past decade or two. So they're continually getting better, okay? And they exploit all sorts of ideas to do this. So there are two parts to this. You formulate a model, and then you send it to an off-the-shelf solver. And you don't write a program to say how to solve it. So just as an example of a formulation, here's for my previous problem, I would have, say, a set of products, a set of network locations, set of links, and here's my data, capacities from I to J, and supplies, and costs for each product shipped from I to J. And this now, in this part of my formulation, I'm just describing the data. The rest of my formulation, I describe the problem. So I say what the decision variables are, amount of product B to be shipped from I to J. I say I write down a little mathematical description of the total cost. We sum over all products and all links of the cost times the amount shipped. And then we have two constraints here. One's an inequality, one's an equality. And one enforces the capacities and the other enforces material balance, essentially. So amount shipped in plus the supplier demand equals amount shipped out. And so this would be a typical model-based formulation. Okay? Now, what I said was that what really makes model-based approach attractive is handling complications. So let's go back and consider some complications. Costs may actually have some fixed part to them. There may be a fixed cost for using a certain link. independently of the variable cost of how much per unit. Okay, it may be that there's a minimum shipment amount. It may be that number of links that are actually used cannot be too great. Okay, and along with this comes some data, some fixed costs, some minimum amount that may be shipped, some largest number of links that can be used. And once it's come out that you need to actually put this into your model, you have to go back and consider what you're going to do in the method-based or the model-based approach. So if we go back to the method-based approach, well, we have to, now that we've made things more complicated, we have to revise or rethink our solution approach to take this into effect. And then we should update or re-implement our program. And what are the challenges of this? Well, in this particular example, by putting in these complications, the shipments have become more interdependent. Okay? What you do with one shipment affects another one because it determines, which links you've paid a fixed cost for and which you haven't, that kind of thing. So, and two different shipments may combine to give you the minimum shipment amount. So it's actually more challenging to build an algorithm than before. And in general, every time you change your problem, you have to redevelop your method to some extent. And unfortunately, even small changes to a problem can necessitate major changes to a method. Your method may have taken advantage of some property of the problem that, due to the change, no longer exists. And unfortunately, as we've seen from the optimization model lifecycle, changes happen frequently. So this is going to be a challenge. In method-based, what do we have to do? Well, we have to update that my objective expression to put in the fixed costs. We have to formulate some additional constraints, and we send it back to the solver. Okay? So the challenges here for this particular example are to create some new variables and expressions and put in some new constraints. I'll show that on the next slide. And in general, the formulation does tend to get more complicated, and a new solver type or solver options might be needed. But just a few solver types suffice for a great many formulations. And in this case, it will turn out that the same solver could be used as was used before. And updating formulations is a lot easier than updating methods. You just have to update your description of the problem. You don't have to figure out a new way to solve it. So I've just put in red here the changes that I made. So you see I added fixed cost variables, and I added a term on the objective to represent the sum of the fixed costs. And I added two new constraints down here in red for two new requirements I put in. And I modified this constraint here to add a third requirement having to do with the fixed costs. And that's it. And then this same thing can be sent back to the solver. Okay. So that's in a nutshell the difference between model-based and method-based optimization. And given that I'm doing model-based optimization, I then can consider what way should I do that. And so I'm now faced with my second part, which is approaches to model-based optimization. And to introduce that, let me say that the real challenge here in model-based optimization is that you really have two forms of the problem. You may have been thinking, as I said this, well, that's all well and good that you describe the problem and then you send it to a solver. But what do you mean send it to a solver? It's just some mathematical terms on a slide, and the solver is a program. So what do you do there? And so what you want to do is translate from the modeler's form, which is your symbolic description that's easy for people to work with, to the solver's form that's some explicit data structure that the solver can work with and quickly compute some solution that's valuable to you. Okay? And again, there are two approaches to this. There's a programming language approach where you write a computer program that generates the form for the solver. Maybe it reads in some data and then it does a bunch of calculations and it calls some API for the solver. Or you can take a modeling language approach, which is that you write that formulation that I had in some form that the computer can read and translate. In other words, you make a computer readable model, formulation language, which I call a modeling language. Okay. And now I'm not going to say a lot about this second part because in this area, the modeling language approach is pretty much taken over. So this is certainly the approach that in most cases people adopt. And modeling languages have proliferated in number and have become more powerful. And the programming language approach is only used for specialized situations these days. So I'm going to skip over a description of why the programming language approach isn't so desirable and why you'd rather use a modeling language that's much more reliable for maintenance and much faster for development and so forth. And I'm going to move on to the third comparison that I want to do, which is between approaches to modeling languages. And you'll see that programming is going to come back. So now for modeling languages, as you may have assumed here, I'm mainly going to be talking about modeling languages that are called algebraic modeling languages that are designed for that algebraic formulation that I showed in my example. Okay? And when people talk about modeling languages for optimization, this is generally what they mean. In principle, you could design a modeling language based on any way of representing an optimization problem that's understandable to people. But the ones that are used most and that are most general are these algebraic formulations because they're a good fit to all sorts of applications and they're also a good fit to the solvers. And so they're really quite versatile. And as you'll see in the case studies, can be used for a great many different kinds of problems. Okay? So again, there are two approaches, and I'll describe them as the executable approach, where here comes the programming again. You write a computer program that resembles an optimization model and that you can execute to send the problem to a solver. So we basically take that mathematical symbolic algebraic description that I had before, and I figure out a way of writing that inside a programming language. Okay? And the other approach is what I call the declarative approach, and that is you take a language that's designed for optimization and you use it to write a description of the model. Okay? And then you run it through a translator that translates it along with the data to the form that the solver needs. Okay? So it's more purely declarative rather than being a program that you execute. Okay? So now in the last part of I'm going to describe more generally the difference between these. And it's hard just by hearing me say it to appreciate how these are different. So I'm going to start off with an example. And I'm going to go back to that supply chain optimization. And for the executable approach, I'll use Gurobi Pi, which generates problems for the Gurobi solver. And it's based on the Python programming language. And it's designed to look like algebraic notation inside Python. Okay? And for the declarative approach, I'll use my AMPL modeling language. And it's based directly on algebraic notation designed specifically for optimization. And it generates problems for Gurobi and also for other solvers as well. So I'm going to use a simplified form of the network. And so here's the data again. And now I'm just going to focus for this current purposes on here are these different sets and here are the capacities. How do I write that in Gurobi Pi? Well, I write some Python lists and dictionaries. So you see here I'm using data structures of Python to represent this data. In AMPL, it's more declarative. You would say, well, there's a set of products, there's a set of nodes, and there's a set of arcs within the node pairs. There are capacities, one for every arc. You would define what your data look like. And then at some later point, you would separately say what the data values are. So you have sort of a symbolic model, and then you have explicit data. So because it's a language that's specialized to modeling, it can maintain a much greater model data separation than when you're working in Python. And you can see these definitely look different. And now look at the variables and the objective and the constraints. This is just a repetition of what I showed before. And let me now show what that looks like in Gurobi Pi. So this is the executable approach. And I define a model object. And then I use an add vars method to add the variables. which are called flow. In this case, the objective is sort of given with the variables. But you see here, I've added 2 constraints. And there's an add constraint method. And if you look inside this add constraint method, you see something that looks like a constraint equation. So you see here was my equation in mathematics, and here it is in Gurobi Pi, and you see the 2 summations correspond to these 2 summations. This parameter corresponds to that. For all products and nodes corresponds to all products and nodes. So you see how they've been able to cleverly make Python sort of look like an algebraic expression. That's the idea. In AMPL, I would say we define the flow variables, non-negative. We explicitly give the summation that gives us the total cost, and then we give the 2 constraints. And you can see here that I've been able, because this is designed for optimization, it's possible to make it look more like optimization than I can do in Python. Okay? And so I have maybe more direct correspondence between the constraint here and how it's written algebraically. So then let's see what happens when you want to solve. Well, once you've run all those Python commands in Gurobi Pi, that has actually generated the whole problem, the whole optimization problem. So then you just use the optimize method to optimize, and you run some Python statements to show the results. And so the optimizer tells you that it solved it, and it gives you some results. Now, in AMPL instead, what you do is you describe the model and you describe the data, and then you read those in. And when you've read them in, now in memory, there's a description of all the model and the data. And when you're ready to solve, maybe you have to do some more data manipulation. Then you say, use Gurobi solver and solve. And only at that point are they put together. And the problem is solved. See, Gurobi comes back. And then you can say, display the variables, and it will display them. So because this is like an optimization system, it has some specialized commands just for conveniently letting you look at results of optimization problems when you're developing your model in the middle of that optimization modeling lifecycle. So that's an example of running the 2. And now I'm going to conclude this part by now comparing the executable and the declarative approaches. Oh, let me just say that if I want to switch to another solver, I can switch to another solver. So here I use a different solver instead. All I had to do was just tell it to use a different solver. So the executable approach, the concept, as I said, was to redefine some operators in the programming language so that they're actually they actually create constraints rather than just adding and comparing numbers. And this lets you do the complete application development in one language, say Python. Okay? And it does give you some direct access to advanced solver features if it's something like Gurobi Pi that belongs to a particular solver. But the disadvantages you have are that, of course, Python was not really designed for describing models. It can be awkward at times. There are efficiency issues. Gurobi Pi actually has 3 different ways of writing sums, and which you use depends on your convenience and also on how difficult the sum is. You know, and then there's sort of a confluence of modeling and programming bugs. That if the solution comes out with all the variables 0, you don't know if your model is wrong or if you messed up some loop index or something else. It can be a little difficult for that reason. In the declarative side, this would be like the AMPL approach. I said we describe a language for optimization models, and then to connect to alternate external applications, there are extensions for writing simple scripts where you can write essentially simple programs using AMPL notation just to do things like a series of solves or to print something on some condition. And then for general sort of deployment, AMPL has APIs to different programming languages. So a variety of programming languages can be used. The disadvantage of this is that it does add another system between the application and the solver. but it is designed for building and using optimization models. So you're sort of using the tool that's appropriate for the job. And it's not specific, as you saw, to one programming language or solver. So basically, AMPL is a tool that can be brought to bear if you're using almost any popular language, okay, and any popular solver. So it doesn't have that limitation. You don't have to at the beginning of the project where you're not quite sure what formal model you have or what will solve it best, you don't need to commit yourself. Okay. So 2 more slides on this. How does this affect integration with applications? Well, Gurobi, everything can be developed in Python. It's part of the Gurobi package, so it sort of puts everything together. Okay, your whole application in Gurobi. And if you don't want to use Gurobi, there are some solver-independent alternatives that use Python as well. AMPL, you develop prototypes in AMPL, and then you can extend that prototypes with a few simple loops, tests, and assignments, and then you use the APIs. So this is pretty much what I said. And what about integration with solvers? Well, Gurobi Pi worked closely with the Gurobi solver. So this particular kind of executable approach is great for exploiting a particular solver if you know you want it. Whereas AMPL supports all popular solvers, and it extends to things beyond any particular solver. So Gurobi is a linear quadratic solver, but AMPL extends to nonlinear solvers more generally. It extends both to local nonlinear solvers and global nonlinear solvers, which work very differently. And so it has this broader solver support as opposed to specialized solver support. So I hope that gives you some idea of what model-based optimization is. And I'm going to spend the remainder of the time going through some case studies. Okay, and I'll just say briefly, I did make a list of all the different kinds of applications. There are quite a few, and if you looked at any other modeling language or any of the solvers used with model-based optimization, they would give you a similar list. But today I'm going to show 4 of them, and a very diverse applications. So the first one has to do with packing shipments. Okay? And the packing problem is that Young's plant farm is actually a very large operation that grows plants of many kinds and sizes. And it has a whole net fleet of trucks just to ship, and they have very large customers such as Walmart. So this is quite a large operation. It's doubled in size in the last 5 years. And so in order to ship these things, the plants are packed on special huge rolling racks. And you can see a picture of the racks here. And so the problem is to generate good plans to pack plants on these racks every day in order to ship them out efficiently and finish the whole process in time to get the orders out. So their business has expanded past the point where this can be done easily by hand. And in fact, they originally just had someone with a spreadsheet assigning things based on what looked best. Okay? And that sort of got to be too hard, so they turned to the idea of an algebraic modeling language plus some kind of a linear solver like those Gurobi or Express or Cplex that you might have heard of. And they chose a modeling language approach to get much better solutions this way, and to get both faster solutions, to load the racks faster, to use fewer trucks. There are quite a few economies of just being able to generate good solutions quickly, okay? And both because the solutions were better and because they were generated quicker, and because they could then switch solvers. At any given point, they could benchmark the solvers and decide which to use. So because I have only limited time, I'm going to read these slides in here that describe the formulations. And the whole slide deck will be published if you'd like to review these, but I won't go through them every day. I just want to say that among the data for the Young's platform problem is up to several million different patterns in which they could pack those racks. Okay? So before the optimization is done, a pattern generation application is run to generate good patterns. Okay? And then basically the objective is to minimize the racks used, plus some penalty terms that try to avoid on the racks that are not as desirable for some reason. And the constraints, and basically the constraints are just that they have to meet all the orders and fit all, and sort of not spread orders for one company over one customer over too many trucks. Okay, so so the original model was built by a professor at the local university, but it was extended by Knowledge Platform with some help from us to handle larger orders. And the maximum size of the problem can be 100 million variables, depending on how many of those patterns they generated. It's at least hundreds of thousands. It takes 10 to 45 minutes to solve. And they have a spreadsheet application that prepares the data and results of reports. One specialist uses this tool multiple times a day. Okay? And this is basically what they rely on to get their shipments out. Okay? Next one is a design problem from this company called Motion Robotics. You see that they design, among other things, drones. And their goal is to create new drones and maybe new electric aircraft. Okay? And to evaluate their designs over many possibilities, okay? Over different design, different architectures, different flight paths. Okay? And so they originally thought about using spreadsheets, but it was not realistic. They looked at simulation and machine learning and a Python-based sort of specialized design optimization system. But they eventually turned to an algebraic modeling language because they needed the power and generality to be able to specify exactly the requirements of their designs. Okay? And so they chose it because it let them write a formal optimization model and would implement complex equations. It would let them try a variety of solvers, and it would let them deploy this via the APIs to a large number of processors to run many optimizations at the same time. So again, the formulation involves data, and again, I won't go through the formulation slides in any detail. Various kinds of variables, so they formulate, and I'll just say more about the implementation. So it was suggested to them that they should use this approach by a professor at a local university, but the implementation was by two analysts at the Motion Robotics company. And they were able to build prototypes within months and then expand them to more complicated ones with more dimensions. Typical optimization takes 7 minutes to solve, and they tested 5 nonlinear solvers before arriving at the one that worked best for them. It uses AMPL scripts and the Python API to AMPL to embed it in their larger system, which includes wind tunnel data and things like that. And they deployed it so that it could run in parallel on up to 2,000 nodes in a compute cluster, so they can run a huge number of cases at the same time. And then they connected it to various other systems that they use in doing their design. So there we see a quite different approach. And so let me move on to the third one. This is by a company called ABB, which is big in the power industry. And this application is to manage power grids. And here I show a page describing the product that they built using AMPL and model-based optimization. It's called Grid View. I'll make this a little bigger here. And you see that it's uses advanced analysis methodology, combines generation, transmission, loads, fuels, and market economics into an integrated framework. So it's a complex model, and it uses state-of-the-art modeling technology to simulate security constrained unit commitment and economic dispatch. So it's a complex modeling exercise, okay, that's built around a model-based optimization system. And they have to decide when to turn power plants on and off and how to transmit power over the grid. And they want to simulate optimal decisions to support their planning. Okay? So basically, they're considering a lot of possibilities as to what they might do. And each different configuration, by adding sources or retiring sources of energy, they need to see what effect that will have on their entire grid, whether it be positive or negative. So they considered C++ for the entire system, but they found that handling the model in C++ was too difficult. They ended up using a modeling language for the optimization and C++ for the user interfaces. And they chose AMPL for the ease of modeling and because not only was it ease for ABB, but ease for their customers. Customers could look at their formulation and suggest small changes to meet their particular situations. And then they could use the C++ API to AMPL to embed it into this grid view product, which you saw on the slide, which is what they actually sell to people. And so again, I'll go quick through the formulation, various data, decision variables, objectives, and constraints, and just skip to the implementation. This one was also the prototype developed at a university that was close to where the ABB offices were, and then 3 analysts at ABB took it over and developed the full AMPL implementation. And the optimization uses a mixed integer linear solver. There are millions of variables, and tens of thousands of those are constrained to take integer variables. Those are generally the hardest variables. It takes about 10 minutes to solve. And it's been deployed to over 30 customer companies, at which there are hundreds of customer-side users. So this is an example of, unlike, say, Young's Plant Farm, where they developed this, and there's basically at any given time one user who runs it multiple times a day to get the answer and drive their business. Here, it's been built into a product, and the product has then been sold out to different power users, power generating companies, and they run it. Their people run it every day to do these. So then my last case, assigning students to classes, this would seem to be a rather sort of boring example. If it were not the situation that we're in today, the situation being that the New York State schools were closed by COVID-19 in the spring, and now they want to reopen for the fall. And to limit the virus spread, they want the classrooms to hold only a limited number of students, and they're offering something called blended instruction to parents, which said that your child will only come into the school 1 or 2 or 3 days a week. And so now they have a terrible scheduling problem, because they have different students there every day, and they have to be in the same group, right? The same cohort. The idea is to reduce virus spread. You want the same students to come in together in the same room every day that they come in. So they want to create a tool for making workable assignments, and the tool should be usable by individual people in the schools, okay, on short notice. So this is not something that's done at a statewide or a citywide level. Each school has to worry about how to schedule its students, and this reflects the general decentralized nature of education in the U.S., and it has to support all these many people at the same time. Okay? And to give you an idea, there are 2.5 million students in the public schools in New York State, in over 4,000 public schools. So it's a lot of people who could be potentially trying to use this. Basically, the only alternative was to have every principal figure out on their own how to make the assignment. And the algebraic modeling language was used as thought of as a quick way to get this done. It offers fast prototyping and development, flexibility of the solver choice, and a Python API that can be used to build it into a web tool that you can put out to all these principals in all these different schools. So again, I have some description of the formulation, but in the interest of time, I won't go through all the details, but you see, it's just like all these formulations. There are variables, there's an objective, there's some constraints, and I'll just finish up by talking about the implementation. So the development here was done by a vice president at Goldman Sachs, which is not known for its educational activities, in fact, but it was a pro bono project. So basically, he offered to do this for free, and to help out the state, because Goldman Sachs is headquartered in New York, and he actually completed a model for this in just a few days, which is something you can do when you have a modeling language. Okay? And then he had a student assisting him who helped with the initial runs to get this going. to test it out and go through the initial model development life cycle. And then Philippe Brindau from AMPL helped get it up in the cloud, as you'll see. So the optimization involves tens of thousands of variables, but takes only 1 to 4 minutes to solve. Okay? But the way it's deployed is that they built a web tool that any principal or a teacher in the school can bring up, and they can put in their data of the students that they have that they need to schedule, and they can click submit, and that just sends in their data and asks for a solution. And at that point, a Python application parses the data, and it runs AMPL in the Gurobi solver. And where does it run it? Well, it actually fires up a new container in Amazon Web Services to run this submission. So automatically, when they press submit, a container is fired up. It contains AMPL, it contains Gurobi, it contains a Python program that runs them. And the data is passed over, and the problem is solved. And then the results are passed back, and the container is destroyed, and the data is thrown away, and the results are back to the user. And this entire application was built in about 2 weeks. So it shows that when we talk about quick prototyping, it shows the possibilities of doing this when there's a need for something quickly. Okay? And so that's the shortest time frame I know of. So that brings me to the end of my examples. And so I'd like to return now to answer any questions that there might be.
Wonderful, thanks, Bob. That was great. Now onto the Q&A. We start out. Our first question, Preeti Ray writes, how to model stochastic demand with normal distribution in AMPL? So in AMPL, you can model stochastic demands in a number of ways. If you're really writing a stochastic program with recourse, you can model the deterministic equivalent and solve that. You can take advantage of some solvers' special decomposition methods for that kind of problem. Okay? If it's just a matter of generating stochastic demands, then there are easier ways to do that. If you're not actually solving what's called a stochastic program, but it's sort of more complicated. I'd be happy to provide more details directly about what you might do there. Wonderful. Second question of 2 questions from Jacob Feldman. First one, what skills are expected to write algebraic formulations? What would you offer to subject matter experts, not scientists or programmers? So basically a technical background is what you need. We see users that don't have anyone who actually studied optimization, but they studied some kind of engineering or computer science, something like that, so that the idea of the formulation of the optimization problem is something that looks familiar to them. Okay? The mathematics is something out of beginning calculus, and so it's something they can do. So I'd say that a technical preparation is needed, and a background where you've actually taken an optimization class or you studied some related field like industrial engineering or operations research, that's even better. But it's basically that technical background that gives you the familiarity with math models. Now let's see, could you repeat the second question? Yeah, it was, what would you offer to subject matter experts who are not scientists or programmers? I think you kind of answered that within your question. And Jacob, if you have a second follow-up to that, feel free to put it in the Q&A. And again, we have about 10 more minutes, so if anyone else has any other questions, feel free to put them in the Q&A as well. Let me just say that so the part about programmers, I mean, the whole idea is you don't need to be a programmer to use a modeling language and do model-based optimization.
it's not, some programming maybe, somebody may eventually need to do some programming to deploy your solution, but you don't need to be a programmer, and that's one of its big attractions.
Great. Another question from Jacob, which came in prior to, would you consider to offer ample SaaS optimization engine available from a cloud as a pay-as-you-go service?
Yes, we have sort of an internal prototype of that. It's tricky to collect the payments, so we're basically at the point now of figuring out how that could be done.
Oh, interesting. Very good.
Meanwhile,
Kenneth Harrison asked.
Yeah.
No, go ahead. Keep expanding on that.
We have lots of people who use it in the cloud, okay? But they have to set up their own cloud arrangement. So something that definitely interests us would be to do that. And if you just want to try it out, there is something called the Neo server, which lets you use all these things for free, by the way. And
okay.
It's just neoserver.org.
Next question is from Kenneth Harrison. Way to convert AMPL model to a written form, latex, Word in parens.
Well, I don't think there's any good app for that right now, but it's been asked a few times, and I think it could be done, but I have to admit that there's nothing in place right now.
Wonderful. Last question, at least the ones we have so far, is from Alok Kumar Singh. He says he's a post-grad student at NIT in India. My question to you is how is it different than Lingo software for optimization, since we use both in our college?
So Lingo is another algebraic modeling language, and so it's different just in how it's designed, what the details of its design, the power of its design, okay? But the underlying idea is the same. The other difference is that Lingo was designed mainly to work with a particular solver that was created by the same company. So Lingo is sort of a modeling language solver solution. And this contrasts to AMPL, which was designed to be independent of any particular solver.
Next question is, I observed that nonlinear solvers are taking too long. Is it really the case, or are there some ways to reduce the computation time?
So nonlinear problems in general will be harder than comparable linear ones, but it's very application specific. But if your particular problems are taking too long, then you could look at some options that the particular solvers offer, and is one thing. So, but what I really recommend is that all these solvers, if you set one certain option, will give you a lengthy log of what they're doing, and I find that when looking at that log, we can often see like what's the best way to try to get better performance out of the solver on that particular problem. Where is it? What is the reason that it's slow? Okay. And there are a number of different reasons that the solver can be slow, and the one that applies is different for different applications. So typically, what I recommend when someone asks me that is, send us the log, okay, and ask us if you need to know how to get it, and we'll have a look at it and see what we can suggest to you. And if it's in a case where it's really difficult, we can bring in the developer of that particular solver.
Great. Next question is from Carlos Jimenez. Do you think the modeling approach is the right choice because computational power is growing faster, parens Moore's law, and programming approach will become obsolete?
Yeah. So there's no doubt that the increases in computer power favored the modeling approach. I know that when I started out in this, one of the big criticisms of it was that it would take forever to translate the model and send it to the solver. because it was so difficult. And now we don't think that it's so difficult anymore. And that's definitely helped a lot, and it's helped the solvers as well. Okay. Now, so I think that the programming approach, I wouldn't say that's going to completely disappear. There are specialized cases where people still use it for algorithm research, where they're mostly working with test problems. They use it occasionally where there's a small and fixed optimization problem that's embedded in some huge algorithmic scheme, and that little problem is never going to change, and they just want to make it as absolutely fast as possible. But I think that the model-based approach has taken over for the development of applications like you've seen in the case studies, where somebody actually has to do more than just take a model that's already known and figure out how to solve it as fast as possible. They actually have to figure out what the model is and how to make it usable.
Great. Next question. We have Kenneth Harrison again. There's so much thought and structure to AMPL. Would be lovely to have a data viz BI tool to exploit the structure of AMPL in an almost automatic way. Any plans on that front?
Yes, we are hoping to do that sort of thing. But I can't report anything really specific at the moment. But certainly, given that we have all that structure, we'd like to be able to communicate as much as possible, much of it as possible, to solvers and take advantage of it where we can. There are a few cases I could point to that structure actually is used already.
Great. Next question from Alan Craven. Are there any plans to publish a new version of the AMPL book?
Not in the immediate future, I'd say. I would like to rewrite the book and augment it, but it's a big project, so I'm waiting still for I'd say the right year to come along when that should be my main project.
All right. Ting Ting Jiao asks how to integrate the AMPL model with a simulation-based performance evaluation for each feasible solution. Some applications need the simulation software to capture more details of the system behavior responding to each solution.
Yeah. So there I recommend using one of the APIs. An API is an application programming interface. It's basically an object-oriented interface to AMPL that lets you make AMPL part of some larger system or scheme, and so you can write a controller that runs simulations, and that also takes data from simulations and runs optimization problems. Takes data from optimization problems and plugs them back into simulations, any combination you want. And that's generally what I recommend to people who have a need to combine optimization with another major tool.
Last question is from Alexander Galenko. Do you have any references to recommend proven designs when building cloud-based solutions within optimization functionality?
Not offhand. I mean, you can find people who've done it and who know how to do it, but it's hard to find someone who's like explained how to do it. It just seems to be changing so fast. But if you write to me, I could ask around our people and see if there's something that we might turn up.
All right, I'll actually give the last question. It just came in, and then we'll any other questions we will work to get done offline. After modeling and optimizing a problem in AMPL, how can we visualize it? Charts, graphs. Is there any way to do it in AMPL?
No, AMPL itself does not have a visualization component. And again, there we point to the using an API basically. I mean, they're like any number of visualization tools in Python, say. So you can write a Python wrapper that calls AMPL and then takes the data, tracks the data back, and then uses some appropriate tool to do the visualization that's really designed for visualization. So just like AMPL is designed for optimization, there are tools that are designed for visualization. And I think the sort of the message is, use the right tool for each thing. That's been our approach.
That's great. I appreciate that, Bob. Well, I want to thank everyone for joining us today. On behalf of Bob, AMPL Informs, I thank you for being a part of our webinar. A recording of this webinar will be available on our YouTube channel very soon. I encourage you to join us for our next webinar on September 9th. Thank you very much, and have a wonderful rest of your day.